isn't it? The red line is a theoretical prediction of black body radiation from Max Planck. Okay, these little points are actual data points. Yeah, they took a lot of data points because, you know, when you build a satellite like that. In fact, they've even got more data points than this. And the story is this, that you could not see the theoretical prediction underneath the data. They took so many data points that they covered the line entirely, and the theoretical line could not be seen. And so the scientists actually enlarged the error bars. I don't think that's the original graph, right? But they enlarged the error bars so that you could see the theoretical prediction. Yeah? Little graphing problem there, right? So this is what we would just say a remarkable fit, right? So now you can have any theory you want of the universe, but it has to have somehow, it's got to put in all directions a fiery wall. There has to be a warm, the radiation given off by a hot object in all directions. Well, you know, there's only one theory that really does that, and except for Chris Murrayism, right? Yeah.
Murrayism has a fiery wall?
Yeah.
What?
Say it again? Oh, it just, the universe was created with this radiation intact. Yeah. Question no more.
Kind of off topic, but is this like the first time a scientist ever really got it right the first time?
No, there's other ones. I don't know.
That's like,
Quantum.
I feel like this is the only story we've ever heard in physics where they're like, oh, what do you know? They're exactly right.
No, quantum electrodynamics is like making predictions that are like, you know, accurate to part in a tenth of a billion. So. Chris Murrayism is, of course, 100%, right? So this is 1989, right? They measure the cosmic microwave background radiation. It is isotropic, which means that anywhere we look, there's no trend. It's all about the same, which is what you'd expect, because anywhere you look at the origin of the universe, right? It has a Wien temperature of 2.736 kelvins, right? And it is exactly black body as predicted by the Big Bang. And I think there's a place in your notes for this calculation. So what is the wavelength of 2.736? Let's figure that out. What is that? It looks to be, doesn't it look to be a bit longer than 1 millimeter, doesn't it? Doesn't it? Yeah. So let's look at, let's see what it is, right? So plug it in, go 2.9 E minus 3 meters Kelvin divided by 2.736. What is that? What is the wavelength of the peak divided by 2.736? And I'm getting, when I do this, that wavelength is about a millimeter, 1.0599 times 10 to the minus third meters, right? So that's 1.06 millimeters. And that's sort of what we thought it was from the graph. So when we say the peak, that's what we're talking about, right? And when we say that it's microwave, these wavelengths are in the microwave range. Yeah? Remember the whole electromagnetic spectrum? Radio waves, microwaves, infrared light, right? These are in the microwave range. These are much shorter than radio waves, yeah? Okay? Okay, so let's just keep going, okay? Here is another prediction, and this is somewhat obscure, but this is something that the Big Bang predicts, and if it's not true, then the Big Bang is not true. Okay? If the universe emerged from a singularity, doesn't that mean that the universe was once very small?
Yeah.
Like as small as like an electron. Aren't small objects governed by quantum mechanics?
Yeah, they are.
Indeed they are. So aren't small objects Heisenbergly uncertain? Okay, so although we say that the peak black body radiation should be the same no matter where you look in the sky, really there should be a minuscule fluctuation exactly equal to the Heisenberg uncertainty at that point. And you should be able to see that. If you look at the sky, you should be able to see some places a little bit hotter and some places just a little bit cooler, but not really very much. These are very, very tiny fluctuations, minuscule ones. But you ought to be able to see it, and it should be what Heisenberg uncertainty principle states, right? So the Cosmic Microwave Background Explorer, COBE, in 1992, they sent another one up, right? And it measures anisotropy. And isotropic means it's the same, right? Anisotropies are places where it's not the same, right? It measures these things, and they are exactly what the Heisenberg uncertainty principle states. And I actually met this guy, George, I think his name is George Smoot. He's a professor in Berkeley, is he? Okay. I could be getting this wrong, but he's a real big wig. I've actually met this guy, and I asked him really stupid questions about astronomy. It's like, why is the telescope at that angle? What's that? He very patiently explained, without saying idiot, at the end of his sentences, right? And when he saw this fluctuation, right? When he saw this fluctuation in the thing, he said it was like looking at the eye of God. Okay. It later was determined, though, to actually be, you were actually looking at data from a satellite, is what the actual answer was. It turned out not to be the eye of God. Okay. But so now we've got a theory. Now we've got a theory, and you can propose any other theory, but here's the data you need to explain. Okay. Why, when you look everywhere, do you see the glowing embers of an explosion? Why is it exactly black body radiation, exactly that of a hot object, but stretched, right? Why does it show signs, unmistakable fingerprints of being radiation that emerged from a quantumly small object? Yes? And why is the universe now expanding? Maybe it contracted, right? So this is just some of the reasons why we think that the Big Bang is really pretty much the only show in town. Okay? So let's just keep hitting the right arrow. Okay? So now the notion is that if the universe expands, it's making something like a four-dimensional sphere very hard to picture. Okay, I can't do it, right? But it should expand, and when you blow a bubble, have you ever noticed that bubbles undulate? Yeah, in 3 dimensions these are called spherical harmonics, and you will learn to love or hate them because you use them to solve equations with electrostatics and stuff like this, right? Okay, so spherical harmonics, the universe itself should have rung, it should have undulated just like a bubble being blown, yeah? And if we see that, it should have a certain series of frequencies. And the boomerang probe, they sent it up there, and it actually measured, these are the error bars there, and that's a reasonably good fit, theoretical prediction. This is one harmonic, this is another harmonic-ish. It's very confusing, right? Okay, so let's just keep going, right? This was a low-res picture. Now we need a high-res picture of this. Okay, so this is the Wilkinson micro anisotropy probe. That's what WMAP stands for. Okay. And this is the really good stuff. Okay, this is taxpayers' money well spent, right? We could have bought a bomb or a bomber or a military ship or sunk some money into the war in Afghanistan or something like that, right? But instead, we looked at the origins of the universe, right? And this is what we know from this. And they know this from, by the way, geometry. They just looked at the geometry. They know how big these features are on the surface of this big fiery wall, right? And they measure here and they measure there. They know the length of these sides, and they're just doing Euclidean geometry on this stuff, right? The universe is 13.7 billion years old. Okay, it's actually now 13.7 plus 3 years. Okay, 5 years, right? Okay, plus or minus about 200 million years, right? That's pretty good, isn't that pretty good? The universe used to be like 12 billion, 13 billion, 15 billion years, right? Now it's 13.7 plus or minus 0.2. Okay. And this is somewhat outdated. Your textbook does not reflect these things, right? It's composed of, and this is a little bit, we'll talk about this later, okay? This is a little bit embarrassing. 4% matter, that's the stuff we understand. 24% dark matter, we're not exactly sure. We got some idea what that is, maybe, but not totally. 74% dark energy, we have no idea. Don't know. We reach it that. We have some idea. But we don't know which of the ideas that we have is it. Yeah? Yeah? We think this might be why the universe, which should be slowing in its expansion, is now actually expanding faster and faster. Yeah, probably that. Don't get that, right? Okay? But here's the Hubble constant, 70.1 kilometers per second, plus or minus 1.3. Not 50 or 100, as some researchers suggested. And the universe is flat. Okay? It's just as flat as can be, and of course we think this is because we're just seeing a very small part of it, that it's just huge, right? The Earth looks flat if you look at a small part of it, doesn't it? Yep. It's so, and the prediction is that we can see about a proton's worth of an Earth-sized universe. Think about that.
Wow.
Yeah. So if you thought you were big stuff before this class, right? Remember, you're just a little tiny thing on a planet that's just a dust mote in solar system, right? Yeah, isn't that right? Okay, our solar system is just one star, not an unusual star in 100 billion stars of our galaxy. And our galaxy is one of 100 billion galaxies. And then that galaxy is a proton's worth of an Earth-sized universe. So, just settle down.